or some essential principles that are relevant. Let's share here the entire screen. Now we found this. Okay, so essential elements that are useful for us regarding the vectors and matrices. We can, I just want to briefly go very fast with regard to these. Wait a second. Okay, so I just want to switch between MATLAB and this material. Okay, so to understand the images, we need, in fact, some basics on vectors and on matrices. And a matrix, it's a construct or it's an array of numbers as shown in here. It can have n rows and m columns. Each element in a matrix, it can be denoted as Aij. A matrix, it can be, we can calculate the transpose of a matrix, as we can see from here, or we can also see, let's do it like this. So we can construct a matrix A, which is a random matrix, which is 3 to 4. So if we evaluate this, the matrix A is going to be the following. So we can make up a matrix where the maximum value it's 3 and it was 4 by 4. Now this can be, maximum value can be 13, which is 6 by 6, and this is the matrix that we can come up with. And in fact, some elements that we're going to see and use when we deal with matrices will be the following. So we can define a matrix B, which can be matrix A from 1 to 3 and from 1 to 4. So with this one, what we can do, what we are really doing here, we randomly generated the matrix A, and in fact, let's clear all. So the space where we have these variables, let's clear some of them so that now they are gone. We can generate the matrix A again. This is how it looks like. And we can also come up or produce a matrix B, which the way that we read it here is that we are reading rows from 1 to 3 and columns 1 to 4. So this is how we can read the B. So B is in principle is the first 3 rows and the first 4 columns. C can be written as A, which can be let's say rows 4 to 6 and columns 2 to 4, which means that we have extracted from the matrix A, we have extracted rows 4 to 6, which is and columns 2 to 4. Columns 2 to 4, so we are extracting this line 4 to 12, 11 to 9. So this is what we are extracting out. And we have also the 6, 12, 5. We can define C transpose, which is like this. So C, it was here, and C transpose, it's shown in here. So transpose is just the symmetric, the reflection of the matrix with respect to the diagonal. Now, this is a square matrix. Now, let's see what B was. B is not a square matrix. We can define a B transpose, which is going to be equal to B transpose. Transpose in MATLAB is just so, and these matrices, B plus B transpose, we cannot add these two together because they are not the same dimension. But what is very important in image processing and also in the properties of matrices is that if we multiply B with B transpose, we are going to get a symmetric matrix. And we like symmetric matrices a lot because those are diagonalizable. The eigenvalues are real values, and this can have some useful applications later on. So these are some concepts or some principles that we can generate. or that we can discuss. Now, similarly, we can have another matrix, which is AA. This can be random number generated, random integer generation, I. This can be, maximum value can be 200, and the matrix can be 300 by 300. If you click this, this is what we see, and we call this one AA. Now, this AA as a variable, it is double variable. Now, AA, we can, let's try this one, AA8. This is equal to unsigned integer 8 of the AA. And what we're doing here, we're just defining a new variable where AA, it is type double, and AA8 is unsigned integer 8, but it's again a matrix 300 by 300. Now, what we can do with these is that we can see, if we do here, no, it should be int show AA unsigned integer 8. So this is an image that we just came up by generating random numbers, and of course there is no pattern in here, and since there is no pattern, we see that it's purely randomly generated pixel values. And if we check here, rotate data, there used to be an option to read all the values. Wait a second. Oh, okay, we can do it. So apparently we can move across the image, and we can read 3 scores, which are RGB, and RGB stands for red, green, blue. And apparently, actually we should not have an RGB, because the number or the image that we have generated, it is black and white, and it is grayscale. But somehow this is reporting RGB values. But if you notice carefully, the RGB values are all equal to each other. So in principle, if you see a complete equality, actually it might be hard for you to see this one, but you can do the same operations that I'm trying to follow in here. Wait a second. So this was. So we are just coming up with an image, which in principle is composed of a matrix, which is composed of randomly generated numbers, and we obtain an image which was 300 by 300. We can come up with something which is 1000 by 1000, and we can call this one BB. And this BB, it took some time to print this one. This is 1000 by 1000 double. We can make this unsigned integer 8, so we can change int 8 of the BB. Here we have it, and we can have a second figure, int show, which says show the image of BB, but as a variable unsigned integer 8. Now, this one, it is. So this is figure 2, and this is figure 1, and it looks like figure 1, it was relatively smaller. It was, I forgot, like 200 by 200 pixel size, and this is 1000 by 1000, so this is a higher resolution image, but again, it's not that it's carrying any significance, because it's just randomly generated numbers. Now, but as we saw here, these images that we're dealing with, it is essential to have some general or knowledge regarding the matrices, because that's what an image is. So this image is just an array of numbers, a two-dimensional array of numbers, where the value of each pixel or each cell in the matrix, it denotes a specific intensity score. And in fact, there is another way to show these images. So we had here figure 1, figure 2, I don't remember how we do this one. Figure 3, I think surf LBB8. Okay, so this one, in fact, it's very hard to see this, but it is since this is randomly generated, it's very hard to notice anything significant. But as you can see, we can see this the three-dimensional plot of this image, where we have on the x-axis we have 1,000 readouts, or 1,000, the numbers go from 1 to 1,000. On the y-axis 1 to 1,000, and on the y-axis we see values or at least intensities from 0 to 200. But probably it is best if we do something in a better way, which would be the following. I'm sharing the screen so we can check here for a house, and or we can check for square. This would be more relevant, and these squares that we can extract. So we can pick this one or this. Save images. This is chapter 2 material. Download PNG. So we can read this image. We can call this one image 01. This is equal to, this is imread download.png. So we just want to read this image whose path it's in the same folder where we are working on. So let's do it like this. Image 01. So this image 01, here we have it, img01. So we just read this download.png, which was just a square, and as a figure 4, we can write this one, im show. We look at the type of the variable, this unsigned integer 8, which means that this is an 8-bit image. An 8-bit image, this means 2 to the power 8 different quantized intensity levels. 2 to the power 8 quantized intensity levels. This makes for 256 different levels. And here, let's show here img 01. So figure 4, this is what it is. Okay, it's not what we were expecting. Why can't we see anything? Now, let's see, let's plot this again. We have to scale this one. So let's plot here figure 5. Okay, so this image that we try to see, actually we can hardly see the contours, which is a square, which we try to obtain from Google Images. I think we picked this one. And so again, we just try to enhance the edges by using this specific function. Now we can try to plot figure 6. We can do surf L img 01, and now here we have this figure 6, which would be equivalent to figure 3, which was again surf L, which meant that we now want to plot, like if this is a mountain, this is going to show a three-dimensional plot of the XY, where we denote the location of where the intensity is going to be evaluated, and the Z-axis is reading the intensity. Now here we see also something interesting, that on here on Google Images, we noticed we were looking for an image like this, which is this one right here. This is the one that we downloaded. But human perception, when we plotted this one, its absolute value, figure 4 was its absolute value. And it looks like we cannot see much from this image right here. The reason we cannot see much here is that human perception does not do a very good job at low intensity values. And these low intensity values, we don't know actually what they really are, but we can kind of magnify these artificially by plotting this in another way. But if we plot them, when I say another way, we just try to to spread out all the possible values artificially. Okay, so we just did an improvement in the histogram distribution of the pixels. Actually, we're discussing some more advanced topic that we are going to discuss pretty soon, but this is not very does not constitute a very difficult part of the course. So we're just going over once we started discussing this issue of the squares. And now human perception, we could not really distinguish the different pixels in this figure as they are changing from 0 to 16. So actually I can see here that the maximum pixel value is something in the order of 15 or 16. The image, it was 225 by 225, and this is what we observe here. And now what is interesting to also check here, it's also the, wait a second, it's also the histogram. So histogram, it is the, so here we have figure 7, imhist, image 01. So figure 7, we can also do grid on. So figure 7, it shows the histogram, and this histogram is showing to us that on the x-axis we see the intensity of the pixels, and the maximum possible value of the intensity is 255, because this was unsigned integer 8, and on the y-axis we see in fact okay. No. Okay. We can completely close this one again. So this histogram is right here. And from here, we can see that we have pixel values. Most of them are something between 0 and 5, and very few pixels have a value equal to 5. We can zoom a little more in detail, but it looks like we have like 5,000 pixels. They have a value equal to 1. Around 580, they have a value equal to 2. And then 259, they have a value of pixel equal to 259, and so on. Here we have also 253 pixel intensities equal to 4. We have equal to 5. Probably we cannot even see this, but let's zoom in a little more. So pixels that are equal to, okay, I cannot see it. Anyway, forget it. But this was 253, 259. There was a pixel intensities in the order of 3 and 4. Now, the idea of histogram, it's an important concept, because it has we can see this in many applications. But one thing that I can, one traditional question that you might often hear is the following. The histogram, it is a distribution of the values as a function of the pixel intensity. One question is the following: what is the integral of this histogram? So this histogram can have a distribution, can have different distributions, where this can be one of the possible histograms. And the possible question is, if this is the histogram, and this is in fact the number of pixels per unit value, per dx, okay? And this is x. Now, this x, it's a value, in this case, for unsigned integer. So we have an image which is 8 bits, and this 8 bits, this denotes 2 to the power 8 different quantization levels for the pixel intensity from the darkest to the brightest. And now, imagine for a moment, what could be the integral of this histogram? The integral is going to be equal to dn over dx, because this is the y-axis. If we integrate this one over dx, this is going to be equal to, so we can cancel out the dx. So this is equal to the dn, and the integral is the inverse function of the differential. So this will give a total equal to n. So what n is, in this case, for this histogram, it is in fact the total number of pixels that are in an image. So in this case, assuming that we are dealing with this image 01, IMG 01, the n in this case is 225 by 225, 225 multiplied by 225. So it looks like the integral of this histogram is going to be equal to 50,625, okay? But now we can pick a nicer looking image, just so that, because it's good to have wait a second, which one shall we pick? This looks like a good one, but let's see what this save image is. We call this one image 02. Then let's try to read image 02. We have this right here, so we have to read image square. I just want to change the name of the file, so that, or what we want to read, so that we don't get confused of how we read and how we write functions. So the name of the file can be whatever. So we write here, this is equal to read the image of, and this one can be img02. Let's see what we obtain. So evaluate selection, imread. Okay, we don't have the extension. This is .png. Okay, image square, we call this image square. This is the same, 225 by 225. And we can go here, figure 17, so that we don't have the figures. We can have figure 17 is equal to, not imhist, but let's do show image 02. Okay, there is no image 02. This is IMG square. And again, it looks like this IMG square is not good for human perception. Then we just need to, okay, so apparently we just can see the edges. And now we can also do this figure 6 and have here figure 16, so that we can differentiate them. This is IMG square. And it looks like the maximum value of the pixel intensity apparently is something in the order of 35 out of possible 255, or out of a possible 256. But essentially, it looks like human perception, or us, we're not doing a very good job down at the very low pixel intensity values. Now in here, we can also do another small exercise here. So we can say here, figure 16, we can have here figure 16/1, so 161. We can plot here from 1 to 100, 1 to 100, which means that we can plot just one edge. So figure 16, it had, we were plotting, where is this? Let's see, figure 7. Figure 16, this is plotting 225 by 225. And this is what it looks like, which is this figure, no, this is 6. Probably we need to plot figure 16. Where was figure 16? Okay, this was figure 16. And 16/1 is this other image. And we just, as we saw, we just plotted not all the image, but just one edge. So we can selectively plot sections that we are interested in too. And again, this is how we are trying to modify a matrix the same way that we did initially in today's section, where we were cropping, or let's do it like this. So we had this matrix A, B, it was just one extraction out of the A, where we denoted which rows and which columns we wanted to plot. Here similarly, or to print. Here in this case, in a similar way, we just wanted to plot from 1 to 100, from 1 to 100. This is the figure 161, as we showed. Now we can go back to this review of the matrices. Now I'll try to denote the most essential aspects, but here we have some basic operation of matrices and vectors. This is how we can add these. Here, this is how we can define the linear combination of different vectors. Now, this aspect of vectors is not very directly relevant to our topic that we are discussing. This is pure linear algebra with limited application directly in the image analysis. This is the vector norms, but okay. But let me say this one, that often when working with image processing and also some relevant research areas, a good knowledge on linear algebra and also the vectors, they can be used often to define certain metrics to evaluate different accuracies, or metrics to evaluate different, how can I say, different features. So if we want to compare two different features, which could be features that can be extracted from the same image, when you compare those, we need to determine similarity between these components. Now, what can be very interesting is that, in fact, for the moment, let's say here we are looking at vector norm. The vector norm is in fact a measure of the kind of Euclidean norm or Euclidean distance, which means that let's see where this one can be applied in image analysis. So let me see. So A is this here. We can call AA. This is equal to A. A, it's 6, what is this? 6 by 6, so this is 136. Forget how we used to write this one. We can describe the A as a line, but I forget how MATLAB does this. Maybe 36.1. No, okay. I don't remember this. What could it be? So A is this matrix, and because for I equal to 1 to 36, EI is equal to AI. Okay, so here we have the vector B. So B is just a vector which is 1 by 36. Now, here we can denote another matrix AA, which is equal to a randomly generated number where 13 was the largest value, and the matrix was 6 by 6. Now, this is AA, okay? Now, similarly, no, this is too much. What was A? This is 6 by 6. This is also 6 by 6. Okay, AA. And now we can write this again. So for I, we can say BBI is equal to AAI. And oh, this is too much. No, we made a mistake then. Okay, what is the mistake? Wait a second. So I think AA, it was, okay, we should stop. No. What was our mistake? Pausing. Okay. What did we write? This is, yeah. Maybe this should have ended. But so this was A, right? We started with A, and BB, we just denoted this one. Oh no. What did we denote this one? Oh, it was single B, right? Okay, this was a single B. But then what was wrong here? BB. Okay, BB was 1000 by 1000. Anyway, so what I will say here is that often in image analysis, what it is used is that you could have an image of a house, and then you can have another image of a house, and then you can describe the complete image of a house like a vector, and then you can have two images of which are square matrices, right? And they are both houses, and then you can describe both of them like vectors, and then you can check the similarity between these two vectors, okay? And the operation with vectors, it is relatively cheaper computationally to do certain modifications, and this is how we can compare them. And the simplest way to compare two different vectors can be, we just subtract those, and when we subtract those, we can calculate the norm, okay? So that could be the one way to do it. And similarly, let's assume that we have C1, which is a vector C1. This can be random number generator 10, 1, 10. So this is one row, 10 columns, and the maximum value is 10. Here we can have again C2. This is another vector. These two vectors are randomly generated. But what one can do is that we can find the difference, C difference, can be equal to C1 minus C2, and this is the difference, and then we can calculate the norm, which is C difference. Apparently the norm is equal to 10.8, and now the norm of C1, this was equal to 21, the norm of C2 is equal to 17, and the norm of the difference between these two vectors, it is very, very close to these because they were randomly generated. But if there was a pattern between these two vectors, then the difference between the two vectors, if they had some similarity, the difference and the magnitude of the difference should be converging to 0. Okay, but in this case it wasn't, for reasons that we try to clarify. And what is also interesting is that this application of converting large images as vectors, this is used in very advanced concepts where you can have two different images, you can mix them together, and then you can separate them back based on only on statistical analysis of the distribution of the pixels. So I want to say that we just mentioned this one as a possible application, but this finds use in much more complex applications of data analysis. And this, if this is done for an image, of course, this can be done for any kind of different data sets. And once they are described as vectors, we can see in the future together in our class that even principles that are very advanced ones in linear algebra, including singular value decomposition or independent component analysis, ICA, or SVD, these can be applied also on images. Once one chooses to describe them as vectors, and then with these vectors, if we want to compare two different features, we can subtract them, we can calculate the norm, we can calculate the angle. So actually this slide, the way to calculate the angle between any two vectors, this is a very important relationship, not only in vectors as in the general sense, but also when we want to separate completely different images. Now, in one sentence, I could say that you can select an image of a fruit, of apple, and you can mix it together with an image of a house, and then just by trying to detect, by doing statistical analysis of the data, we can try to separate those, but assuming that this could be completely different data sets, we may want to conduct the separation whenever the angle between two vectors which can be generated from this data set that we're just talking about, when the angle is equal to 90 degrees, because that's when the cosine can be equal to 0. So these applications there can really be seen by also implementing wonderful properties that matrices do provide. So this is again about the vector norms. Now this concept that you see here, orthogonality, is a very important concept. Eigenvalues, eigenvector, this is the most important aspect of linear algebra as a whole. So here we can determine the eigenvectors and eigenvalues for a matrix. The same thing, we can do it also for images. Here we have an example. This is a matrix which is shown here. You can read here regarding the eigenvalues and eigenvectors. Now I choose to just go over these slides because we can solve this, but it might take a lot of time. Okay, here we are with a very important concept, which is the covariance matrix. Now, the covariance matrix, it is essential, and we're going to see another review session where, not session, but review slides with review materials, where the essence of variance and covariance are very important. Actually, and here you have also an important note which says check the review of the probability. So in that review, we do see this again. And let's see what... so when we are dealing with vectors or matrices, we can still define a covariance equivalent to the images, okay? But now let's move on. Eigenvalues and eigenvectors. Now, the contribution that the eigenvalues can give to image analysis is that often the pixel intensity distribution can have can be distributed in such a way whose major axis of how the intensity values are changing can be determined by using eigenvalues and eigenvectors, because they determine the major axis along a specific distribution. So in this case, here we have two distributions, both are elliptical, and in both cases, if we do a major axis, if we try to determine the major axis, we do find one axis over which the variance is minimum, and another axis over which the variance it is maximum. Okay, so these eigenvalues, they do correspond or are equivalent to the variance. So here, if we see the first graph, the first elliptic shape here, we notice that we have a major variance along the axis E1, and there is a minor variance or minimum variance along the orthogonal direction, which is E2. So these concepts, these are to remind you that whenever you are dealing with these kinds of problems, you can really go back to the, so this was the review on matrices. This is the review on probability. Now, probably it's best for you to go all over these, but an important or essential aspect is the set operations, and the set operations, and the most useful one are these concepts of union, intersection, mutually exclusive complements, because sometimes from complex images, users might want to determine pixels that are part of one component or that are not part of one specific components. And these principles of intersection and union, they are also very useful, especially when we try to determine the edges of a specific image or a specific pixel distribution. We have here the intersection. Here we have the complement. So these are also some important set relationships. You can always go back to these slides and see, because starting from chapter 3, I believe, today we want to start chapter 2, but starting from chapter 3, we can see another detailed, or at least the understanding of these set relationships. It helps us a lot. So we continue again with the intersection. For example, we have an example here. We have the A intersecting the set, the union of B union C. And this one, apparently it can be described as A intersection B union A intersection C, excluding A intersection B intersection C. So apparently we want an equal number of elements on both sides of the equation. Now, a lot of these set relationships, they are more meaningful once we describe this with these diagrams. So we have the set A, which is a set with pixel intensity A. A complement is the one in dark shape. We have A and B, and then we have shown here A intersection B. We have A and B, A union B. So you can go over these diagrams as shown in here. We have also A intersection with B union C, which is the first column in the bottom row. And you can go over these. Now we talk about the random experiments when we try to produce random data sets. And here in this case, we always give the example of heads and tails. So if you have a coin, you throw the coin, then we can try to describe what is the total number of heads and the total number of tails. And we can determine, let's say, a relative frequency of observing heads or relative frequency of observing only tails. And the probability in this case, it's a half, because we can have half of the of heads, 50% of having a head and 50% of having a tail, in case we conduct this experiment for a very large number of trials. So if we do a lot of experiments, we can see that the probability, it converges to the expected value of 50% once we increase the number of trials for large n's. Now let's see here. So here we see some other probability of having different events. Okay. The probabilities. Here we have some exercises, and you can go over these, of course. But let me see how much slides more do we have. 33. We have quite a few. Okay. Now let me see several random variables. Okay. This is the elements that we. Okay. We really do need this. Okay. Where the probability density function. Now we go to continuous. These are random variables, but now we are going to a domain where the variables can be kind of a continuous distribution. And here we have the density function of a specific distribution. Then we see that in the book, we're going to decide the histogram of an image. And this, I'm reading now from the slide, because this is where we're going to see these. And it is strongly suggested for you to go over these slides, because you're going to have also some homeworks, at least that are, you can also find them from the textbook. And you can solve those homeworks if you go over the slides better or in more detail. And now, in this notation that we are going to use, apparently, we are going to have, as it is reported here, L different possible grayscale levels. And we have the PR, this would be the probability of each grayscale level. For example, in the example we were looking before a while, when we had these square images that we obtained from Google Images, we had a square, we noticed that around 5,000 pixels out of a possible 55,000 pixels, they had a score around 0. That means that the probability of having of pixels scoring 0 or 1, it is something more than 99%, 90 or 95%. Now, expected value or moments. Now, moments. The moments, it is are the most important concepts that we can analyze in statistics. Now, if we have a distribution, then the first quantity that we may want to obtain is in fact the average or the expected value. So let's say it like this, so we can have a series of numbers which can be as follows: 1, 2, -3, 5, 17, 19, 22, 33, 15, etc. So this is a distribution of values. We call this X. Now, the first thing that we may be interested to obtain is the expected value, okay? And the expected value, it is 1 over n summing over all xi, where I is from 1 to n. Okay, so this is the, or the, let's say the average value, okay? And then the second most important aspect is we want to determine what is the sigma, or what is the standard deviation, which is in fact is the square root of the variance. And the square root of the variance, it can also be written as xi minus x average. This is x average. Okay, we take the square root of this one. This is the variance. Okay, this is the, let's say, this is one of the moments, which is the standard deviation. Then we have another moment, which is called the skewness. Then we have another moment, which is the kurtosis. All of these here, these are moments of a possible distribution. Okay, so let's see. So for example, we have the variance, and the variance is shown here using an analytical expression, assuming that the values of x, they can change from -infinity to +infinity. For discrete values, of course, this is going to be something between 0 and 255 for an 8-bit image, or from 0 to 65,565 if the image is 16-bit. Now, these are, so this was the variance. This is very important, and the square root of the variance is the standard deviation. The skewness, it is a third momentum. I'm not sure if this is, so the we see here the standard deviation is denoted by sigma. I'm not sure, I don't remember. Okay, so these are all the other momentums. So when I say momentums, the other moments. So when n is equal to 2, this would be the standard deviation. When n is equal to 3, this would be the skewness. When n is equal to 4, this would be the kurtosis. Okay, and just for a moment, I can stop for a very short instant sharing the, you are presenting, stop presenting. So in principle, whenever we have a data distribution, the most important thing that we want to look at is the histogram. Okay, so we want to obtain this. But in order to draw this one, the first, what we can do is that initially we can draw it like a Gaussian distribution, which could look something like this. And to do this, first of all, we need the x average. Okay, how do you do it? We just use this expression. So we calculate the x average, which is going to be some value here. This would be x average. The second thing that we want to determine is we want to determine the standard deviation. How much the x is changing at some distance in here. And this will make us possible to determine, and this is called full width at half maximum. Okay, so this would be 1 sigma. Now we need to know this because in chapter 3 we're going to see how averaging affects the standard deviation for images that have noise. So this one, you really need to understand this very well. So this sigma here and this sigma, it is modified. Well, the sigma now, you can assume this one as if sigma is huge if we have some error or if we have some random noise. And to reduce the random noise, we have some tricks, but these tricks we can never understand without understanding this. Okay, so that's why understanding the moments of a distribution, it is essential. So when n was equal to 2, we're talking about the standard deviation. And standard deviation determines how much is this width, okay? And in fact, it is essential also to notice that, not to notice, but to know that a Gaussian distribution, it is any expression which is equal to y times y0 exponential of x minus x0 all squared with a minus sign divided by 2 sigma squared. You have to know this one. Chapter 3 awaits you. So what this determines a distribution which has an amplitude of y0, okay? Because the maximum value of this exponential here is equal to 1. Then x0 determines the center of this distribution. This sigma determines this width of this distribution, okay? So this is a normal Gaussian distribution. So, or how do you call this one? Normal distribution. It's equivalent to Gaussian distribution. So it's something which looks like as beautiful as this. But then what can happen is that this is perfect. But skewness, it's a measure which calculates whether starting from the center, whether this edge is longer than this other edge. So it just compares these. If skewness is 0, that means that the distribution, it is symmetric with respect to the average value, okay? But often this is different from 0, which means that the distribution, it's not that beautiful, but it's going to look something like this. Again, so this could be a short tail, and this would be like a long tail. So here, skewness, we denote this one as different from 0. Now, kurtosis, it's another measure which helps us understand how the distribution is changing, which is the following. Let's assume we have again the same x average, and the Gaussian distribution can look something like this. Kurtosis is 0 in this case. It is different from 0 when it looks something like this, which is kind of truncated for no reason. Okay, truncated, it means that you just take out the tip of the iceberg. So this is a kurtosis different from 0, and also this is a kurtosis different from 0. So it's kind of, you completely remove the tip of a normal distribution, or we greatly exaggerate the amplitude, preserving the same distribution, okay? So now, all of these moments, so I just wanted to, for you, please take note of this. Okay, so this is the plot of a Gaussian distribution, or normal distribution, or Bell distribution. Sometimes they call it something like Bell. It looks like a Bell distribution. And these are the different moments of data distribution. Let's call it this way. Now, do you have any question for what we did so far? If not, we can just do a very short